So in this video, we're going to be talking about unit testing. Unfortunately, I don't have any time to edit this video, so if there are any flubs or flops or mistakes in it, or awkward pauses, I'm sorry about that. We're just going to have to live with it. So before we get into how to use unit testing, let's talk about why we should test in the first place. We want to test our code so that we can prove to ourselves that our code actually works. We want to be confident that our code is going to behave the way that we expect it to behave, and we want to be able to catch bugs early. By setting up this automated test of suites, not only do we not have to keep writing tests manually every single time we make changes to our code, but we can also test smaller portions of our code, which will help make the debugging process a lot easier because we don't have to figure out where in our entire program things are going wrong, but only where in that portion of code that we're testing things are going wrong. It's also nice because when we make changes to our code, we can rerun the test that we've already written, and if we've broken anything, we'll be notified of it then. One of the downsides, though, of testing is that we only know that our code is passing the test cases, which doesn't actually mean that our code is correct, just that it passes the test cases. There may have been some test case that we just forgot to write that would actually trigger some bugs in our code, which is why you end up finding bugs in production code, even with programs that you use. Or maybe when we were writing our test case, since it's code, we made a mistake in the test itself that actually ended up hiding bugs in our program. So again, just because you're passing your test cases doesn't mean your code is actually correct. So then you might ask yourselves, well, why don't we formally prove that our code is correct? If we have this formal verification, we know 100% without a doubt on every single possible input that our code's going to work. But there are some downsides of this. The first is that formal verifiers generally have a high runtime complexity, which means they can only be run most of the time for small programs. They generally introduce some extra overhead for the programmers in that you have to either write your code in a specific way, or you might have to add preconditions and post-conditions to your code, or some other type of constraints as to what's supposed to be going on in order for the verifier to work. And those constraints just might not be possible to specify, or you might have to use a different language than the verifier works in, or it might not be practical to go back through all the code that you have and make all of these large changes. So that's why we tend to still rely on testing, even though it's not as good as proving that our code is correct. There are generally three classifications of testing. There's end-to-end testing, which is where we run a program from start to finish, and we see that it behaves correctly. A lot of times when I'm testing your homework assignments on Mimir, I'm doing this end-to-end testing because I just want to see that it's working correctly, and I don't care how exactly the internals work. There's also integration testing, which is verifying that the different parts of your program are interacting with each other correctly. You might have class 1 and class 2, and class 1 might need to use some methods from class 2, and you need to see if those things are working correctly and that they're able to communicate effectively. Or maybe you have some database in your program and you need to check that you're talking with that database correctly. Those would be your integration tests. And there's unit testing, which is what we're going to be talking about today, which is testing whether the fundamental units of your program work correctly. Generally, when we're talking about unit, it means a class. So we're just seeing if this class by itself, do its methods work correctly? And this is what unit test is designed to do. So what exactly are we testing? We're really testing our expectations. Is our code doing what we think it should do? If we expect that our code should return some y when we give it x, well then we have to check that when we give it x, we get back y. It's not very glamorous in terms of the code that you write, but it does end up being useful in that it's catching these bugs for you as you're going along. And it might seem kind of weird that we're doing all of this extra work because you are going to be writing code to make this happen. but there tend to be a lot of benefits and payoffs for having these tests here, and that they make the debugging process later down the road much simpler and save you a lot of time then. So even though these tests are going to look simple and dumb, they got to be there just to make sure that everything that we're doing is working correctly. Now, for our examples, we're going to be testing the fraction code that we were working on in class the other day. So in order to create a test case here in PyCharm, we're going to right-click on our directory, select New Python File, and then we're going to want to select a Python unit test. In terms of naming conventions, you're going to want to name all of your test files beginning with test underscore, and then generally what they're testing. You want to follow this naming convention so that if we end up using the automated test discovery, which makes running your tests a lot easier, the test discovery is able to find them. We're now going to change the name of our class to be test fraction because we're testing fraction. And here you can see that we're inheriting from unittest.testCase. This is the test case is the main unit where all of your tests get collected together for a single class. And that's inside Unittest. So we need this import for Unittest, which was done automatically for us here by PyCharm. And then PyCharm also wrote for us that we're going to need want to run unittest.main, which will run the tests that are in this file here. Now, in order to test fraction, we're going to need to import it. So from fraction using classes, import fraction. And again, all we're going to test is some very simple things. So the first thing that you might want to check is whether we create our fractions correctly. So test fraction creation. And when you're writing tests here inside of your test class, also make sure they begin with test underscore for the automatic test discovery. So over here, we might create a fraction, say frac1, and it's equal to a fraction 3/4. And so now we have to test to see if we've made this fraction correctly. So we will do self.assert equal. Well, we want to make sure that this fraction 1, well, its numerator is equal to, well, 3. And we want to also check that its denominator, there we go, oops, fraction 1, that's why, is equal to 4. So it's a really simple test, nothing too complicated, but we got to make sure that what we expect is happening is happening. So here you're seeing one of the assert statements that's offered by the test case class. It's assert equal, and it checks whether the first thing is equal to the second thing. Just doing a simple equality comparison, and if these things don't end up being true, then what will end up happening is you'll get an error there. So in order to run our test cases, what we can do is right click and let's see, we might say run unit tests and fraction, not with coverage, run unit tests and fraction. And this will run this fraction class right here because we named things correctly. You can see up here it's using unit test as discover to locate our test cases, and that's why it was important for us to name them with the conventions that files names begin with test underscore, your classes begin with test, and the methods inside the class that you want to test begin with test underscore. You can see that down here we are indeed passing our test case and everything is good. But let's say we had made a mistake. Maybe instead of doing 3/4, we did 3/5. What's this going to look like? So we run again, and we can see that we had some insertion fails. And if we go into our test case for test fraction, and we look at test fraction creation, you're going to see that 4 is not equal to 5, right? The actual value was 4, the expected value was 5, and we can click over here to see the difference. Expected was 5, actual is 4. Though normally, I think it's supposed to be the other way around, where this is the actual value against the expected value. Test that this thing is equal to that thing. You can also add some additional error messages here if you want to say something. Like down here, we can say something like message equals the denominator should be 4. And now when we run our test case, you're going to see that the 5 does not equal 4. The denominator should be equal 4. And that will let you provide any additional information for other people using your test to help them understand what's going wrong. So we fix this back to being 4, and then everything is good. There are other things in the unit test testing class besides assert equals, and I recommend that you look at the documentation for them. They all begin with assert. So if we go over here to unit test and we search something like unit test.assert, oh no, here we go. Skip to the list of assert methods, so we can just check to see if things are equal, if they're not equal, if something is true, if two things are the exact same object, if it's not a different object, if it's none, if it's not done, not none, if the value's in some container, if it's an instance, not instance, and it goes on. You can check to see that we raise some exception, we warn, we do some logging. Check to see if two floats are almost equal to each other. This is really useful again if to get around rounding issues. You have greater than, less than or equal to. There's a comparison against a regular expression. If they have the same number of elements. You have checks to see if lists are equal, if sequences are equal to each other, if tuples are equal to each other, two dictionaries. I highly encourage you to go look through all of these lists because there's a lot of stuff that we're not going to end up using here. So now let's say we wanted to test to see if our multiplication function is working. So def test multiply, right? And each test should only test one thing. So maybe we test multiplying by fractions. So over here, what we'd want to do is create some new fraction. So maybe we have frac1 is equal to fraction 3/4, and then frac2 is equal to another fraction. Maybe it's 5/8. And then when we're doing this for the testing, we can't necessarily use the same methods that we're using in our code to test. We have to know what the result is supposed to be by hand when we multiply them together. So when we multiply the values together, right, we're going to get hopefully 3 times 5, which should be equal to 15 for our new numerator, and then our denominator should be equal to 8 times 4, which 8 times 4 is 32, right? Then don't forget that we simplified these values, but I don't think there's anything here that we can simplify, so this should be our new answer. So over here, we would do something like product is equal to fraction 1 dot multiply fraction 2, and then we will again do another assert equal. Assert equal is probably going to be the one that you use the most because a lot of times you're just checking for equality of values, but again, don't forget about the other ones. So our numerator should hopefully be equal to 15, and our denominator should be equal to 32, hopefully. And then we can run our tests again to see if we get this right. And you can see down here we're passing all the tests, so it's all fine. Now, normally I would think that if we're working over here after we multiply the fractions together, it would really be nice if instead of saying, make sure that our numerator is equal to 15 and our denominator is equal to 32, we could do something instead like self.assert equal our product is equal to the fraction 15 over 32. Now, if we try running this right now, we're going to get some problems because we haven't defined what it means for fractions to be equal to each other. Let's see if we can understand this error message. So we had this failure message, assertion error 15 over 32 does not equal 15 over 32. This is because we haven't quite defined what equality means for our object. And that's why we're seeing they're not equal. So over here, what we could do to make this so that we can compare them using equals, because again, they're just doing an equals equals comparison, is we can go and add that method into our fraction class. And the method that we'd like to add is equals. And we might as well also add not equals while we're at it. So hopefully over here, we should only be compared against some other fraction. And right now, what we should say, is if not is instance other fraction, then probably raise an exception, raise value error. And say something like cannot compare a fraction with other dot underscore underscore class. So we can't compare a fraction with whatever other's class is. Otherwise, what we should do is do something like self.simplify. Well, we don't want to simplify ourselves, but we should make sure that we have, instead of simplify, we want a simplified method, which will give us a copy of our object, but simplified. So simplified self is going to give back a fraction. And now down here, we can do something like simpler is equal to self.copy. Simpler dot simplify, return simpler. And now down here in our equals, else we can say simple self is equal to self dot simplified. And simple other is equal to other dot simplified. And now we just have to return that simple self's numerator is equal to simple other's numerator. And simple, let's put this in parentheses to make it easy to go to the next line. And simple self's denominator is equal to simple other denominator. And now that we've correctly defined equals, if we go back and we run our test case again, you can see that we're passing all the tests. And this just makes it a lot easier to see whether we're getting things correct or not. Now, it's not only a good idea to check to see if what we expect to happen is happening, it's also a good idea to check to see if the bad things that we prepared for, if they trigger, if we can handle them. So what we want to do is def test multiply fraction. Maybe this one would be fraction, and fractioned and bad thing. So maybe our bad thing is going to be a string. It's hello. Maybe our fraction is going to be equal to fraction of 3/4 like we've been doing. And now we can do the assert that we raise an exception. So if we go back to Unittest to see how this works, we can do assertRaises. Pop over here. So there are two different ways that we could use assertRaises. We can do it with the exception that we expect to appear, our object, and then the arguments that we want to pass to it. Or we can do it with a context manager, which looks like it's going to be a little bit nicer. So with self.assertRaises, some possible exception, do something that might trigger that error. So down here, we can do something like with self.assertRaises, and we're expecting it to return a value error when we do fraction1 dot multiply the bad thing. And if we run it, hey, we're still passing that test because it did indeed raise the exception. If we had again made the mistake, so it's say assert not raises. Oops. Let's see, where is this? Well, I guess there is no assert not raises, unfortunately. Nope, doesn't look like there's an assert not raises. So what we would, expect to do if we had forgotten this and it raises an exception, we run this and then we get our exception that gets raised, and that would cause our test to crash, and we would need to go fix it. So let's put that back in there. Assert raises. If you would like to use it the other way, it would look like this. Self.assertRaises, and again, we're looking for a value error. And now over here, we want our callable, which would be frac1 dot underscore underscore multiply, or frac1 dot multiply, and then our value would be bad thing, and that would be the other way of doing it as well. One thing that you're probably noticing is that bad thing over here. It's being highlighted in orange, and this is one of the advantages of using the type hinting. PyCharm over here is telling us that, hey, you should be expected to give either a integer or a fraction, but you're giving me a string, so you're probably calling it in the wrong way. And yeah, we are calling it in the wrong way. One thing that you've probably noticed is that we've used the same fraction, right? Fraction 1, fraction 1, fraction 1 multiple times. If you have some common piece of setup code that you want to be run before every single test, the way that you can do that is by defining a setup method. And I pressed Control-O to get this to appear, so setup. And this is going to be run before every single piece of code, every single test in my test case gets run. So over here, I could do something like self.fraction1 is equal to 3/4. And now I don't need to, frac1 is equal to the fraction 3/4. And now I can do this here, and I don't have to keep defining it in every single one, but now its name is going to become self. And then again, I wouldn't need this here. I could just do self. Now, probably one of the downsides of this example here, in that switching it to use the setup, is that you don't see the fraction appearing in the test case, which might make it harder for other people to understand what's going on. Frac1, right? They might not understand what's going on because they have to go look back in that other piece of setup code. But now we'll have the exact same effect, and all's going to be good. Now, in doing our testing here, it's likely that we would preferably like to test with more than just a single value in our code, but instead test it with multiple values. Now, we could create multiple different tests to do it, but that's going to bloat our tests quite a bit. The other option that we could do is test a lot of values and see if they all meet the conditions that we're expecting. But if we do it that way and one fails, we don't necessarily know easily which one is failing and which ones are passing. So what we can use are what's called subtests. So over here, we might define a new function, def test underscore multiply fraction and int. And we'll use subtest to make it so that we don't have to create a whole bunch of individual test cases, but still be able to easily identify what's going wrong. And I also remembered that I forgot to do our not equal, which is pretty easy. What we should be doing here to make this happen, we can just return, well, not ourself is equal to the other. Pretty easy. So let's go back to that subtest. So down here, first we need to create our test values. So what I normally do if I'm using test cases is to do tests and expectations, and I make this be equal to a list of tuples where the first elements are going to be the arguments that I'd like to do the methods on, and then the second element will end up being what I would like to actually see as the expected value. So over here, what we might have is a fraction, and this fraction might be something like 5/8. And we expect our fraction 5/8 when we multiply it, say, by 2. Well, what do we expect it to come back with? Well, we expect it to come back with a fraction that is going to be equal to 10/8. So over here, arguments to my function. Over here, the result that I expect to get back. So we might do a couple of these. So maybe we have some other fraction, maybe it's 2/3, and maybe we're going to multiply it by 3, and we expect to get back the fraction that's 2/1. Or not 2/1. Oh yeah, 2/1. And then maybe we do one more fraction over here. Maybe it's 9/8, and we multiply it by 5, and we expect to get back 45/8 at the end, or maybe 45/7. And now what we need to do is go through each one of our tests. So for args, comma, expected answer, or expected value, in tests and expectations, we create our subtest. So with self.subtest, it's going to create a context manager, so we're going to use it with the with statement, and now we can provide as many keyword arguments to test to have it show up later on in the test case to help us know which ones we're getting right and which ones we're getting wrong. So over here, I might say my fraction is equal to args at 0, and my integer is equal to args at 1, and then the answer, we can probably leave that one out because it'll print it out in the error message for us. So now we can do self.assert equal, well, fraction.multiply, and we want to multiply, well, we should probably just split this apart a little bit more to make it a little bit easier to work with. So over here, we might say frac integer, and we can now clean this up to be fraction, and then integer is equal to integer, and then self.assert equal frac.multiply integer, and we expect that to be equal to the expected value. So now let's try running this, and we get it all right because our code's working, which is fantastic. But let's say we had made a mistake, and maybe this should have been 45/6 again, saying that we made a mistake in the test case, which again, we also could have had a mistake in our code. If we run it now, and we go over to test fraction, you can see that we have multiple test cases appearing here. And this is where our fraction was 9/7 and our integer is 5. And if we scroll back down past all of this, we have that 45/7 does not equal 15/2. And we're probably getting this 15/2 because our fraction by default was being simplified down. So 45/6, right, that's the same thing as 15/2. And so our answers didn't end up being equal to each other. But now, because we have these values here, we know which was the test case where the problem is occurring in. So we'll turn that back to 7, and all is good once we run it once again. So if ideally we were testing this, we would go through and we would test every single function. But right now, we might want an idea of how well our tests are doing. And to get an estimate of how well they're doing, when you right-click on here, you can say, we want to, run unit tests and fraction with coverage. And this will run the coverage program, and it's going to tell us what % of our lines are actually being executed. So over here in our fraction using classes class, we should be able to double-click on this. And the green lines over here are going to tell us what we're actually covering, and the red is what's missing. So all that red is stuff that we haven't tested, which we should think about doing. if we want to do it, and the stuff that's in green is the stuff that we have actually utilized in our test cases. So we've used simplify, we've used simplified, we've run multiply, but we haven't really done anything in divide, we haven't done anything with add, we haven't done anything with flip or flipped. We've done stuff with multiply fraction and multiply int because it's called for multiply. Apparently, we haven't done anything in divide fraction. You can ignore the comments here. The comments aren't actually really being run, but it's still being counted. And this gives you a rough estimate of how much you still have left to test. And it's probably not going to be feasible for most assignments or most projects for you to get 100% code coverage. So that shouldn't be the goal that you're aiming for, because there may be certain things that are really hard to test because it's with unit testing, because it's a lot of interaction between classes. If you take, for example, the game class that we are writing in class right now for tic-tac-toe, that one would be fairly hard to test with unit test because it relies on a lot of interaction with a lot of the other classes. So it may be really hard to check for things like winning potentially, or like tying, because that relies on the board object being created and initialized and being set up to some particular state. But it can be done, it's just going to be quite a bit tougher, and we might explore that in the next video where we talk about mocking. Now, some other things before we kind of leave here that we should talk about with tests. Oh, one other thing I should mention is that just because you have 100% code coverage, again, it doesn't mean that you don't have bugs in your code, because all of your lines of code, all of your tests might execute all of your lines of code, but there might still be some value that you haven't put as input that causes your code to break. Good examples of this is when we were talking about debugging and we were working with the anagram example. We could have written tests that fully utilized all of our code, but never actually triggered any of the bugs that we had in it if we hadn't given strong enough test cases. So some tips for testing is make sure that each test is really only testing for one thing, and it should be one well-defined thing. If you don't do this, you are going to have very complicated tests that are really hard to understand what the problem is when things break. If you're only testing a single function or a single method in each of your test cases, and that test case breaks, well, you know where your error is at. It's in that test case or method, or potentially in some code that it in itself calls. But if you're trying to test 7 different methods in your one test case, then you now have 7 different methods where the possible error could be at if the test fails. You should also test what should happen and not how something should happen. If your function is supposed to give back some value x, don't check how x is computed, just check that it gives back x. If you were looking with our examples with the multiply tests over here, we weren't really concerned with how the values got multiplied, just that they got multiplied. The other kind of thing here, which is somewhat one of the weaknesses, I think, in my opinion, of testing, is that you have to manually write out all of the answers. You can't rely on the code that you're using to compute the values. So we couldn't write the code here to compute our new fractions products numerator or our new fractions products denominator, because that would have been the same code that we actually wrote to do the computation. And so you can't test yourself against yourself, because you'll always be right and you're never going to get the wrong value. So you actually have to manually come up with what the responses are supposed to be from that function, which generally means you end up doing small test cases, because no one likes to write gigantic test cases because it's way too much work. But something to watch out for there. You also want to make sure to include tests that test edge cases in addition to the average case. For example, if we are sorting something, make sure that your sorting algorithm works with 1 item, 0 items, a sorted list, a reverse sorted list, lists that don't contain numbers if you're trying to be able to sort anything, containers that aren't lists to make sure that you handle that. In addition to probably like the average test case of random values. We also know that off by 1 errors are a fairly common thing when we're programming. So you might want to test those things that are like close to the edge. For example, in our tic-tac-toe game or in Battleship, you'd want to make sure that you're able to play like right in the corners because they're on the edge of the board, and if you're off by 1, right, it's likely that you might go out of bounds on the board. Or you might also try going just slightly out of bounds of the board and make sure that that gets detected as being out of bounds of the board and not on the board itself, and that you don't have those off by 1 errors. So test all the crazy stuff that's legal and can happen. Don't just check the expected case, because that's how you'll miss a lot of bugs. Make sure that you know that if your code has if and else statements, your code actually executes every path through those if else statements, right? The code coverage for that test, for that function is 100%. Don't just write all your tests so the only tests go through that one if statement and never enter the else, because that might hide potential bugs in the else statement. If you know that the function is supposed to return a finite set of values, make sure that it returns all of those values. A good example is a function that returns a bool. Make sure that you check it when both returns true and it returns false so that it's working correctly. It's also important not to only assert on the positive, but also to assert on the negative. So when you do something, you shouldn't only check that what you expect to happen happens, but you should also check to expect that nothing else happened in addition to that. For example, in Battleship, if you shoot location XY, you need to check not only that you shoot location XY, but that none of the other places have been shot at. Or if you place a ship from 3-4 to 3-7, that your ship ends up at 3-4 and 3-7, and that everything else was the same where you did not place the ship. Or if you come back to our fraction example, it's not something that we did, but we probably should have checked that we didn't accidentally modify each of the numerators or of the denominators in our test cases. Because if we had accidentally written our multiply method to where we modified them, our test cases currently now would not catch that error. So we could make some helper function and check to see that our values are the same afterwards. So over here, after we multiply fraction 2, or fraction 1 times fraction 2, we should probably also assert equal that self.fraction 1, well, it's still a fraction that's 3/4, and it hasn't changed. Because if we had made that mistake and accidentally modified our fraction, the test case without this would not have caught this problem. So that's really something to watch for. Or down here, after we multiply that the values match, but again, still assert equal that, fraction, kind of bad here. What we might want to do is make a temp before we do it. So say something like original is equal to fraction. And then here we have frac.numerator and frac.denominator. It's really important that we don't do this, original equals frac, because if we do this line, original and fraction refer to the same object. So this check that we have down here, that fraction is still equal to the original, would always return true if we had left this statement in here instead of creating the copy of the object that we've done right here. So get rid of that. And again, we should still pass because we wrote our code correctly in class. But again, we don't only want to check what we think should happen, but also that nothing else happened. And this, checking that nothing else happened, is a really common thing to forget to check. Finally, let's see what else we have. Again, you can create helper functions that are not test if you have some commonly used code. Same thing, like you can make methods on your classes that if you're repeating lots of common code or common tasks, put those in the methods. Just make sure they're not named test underscore and they won't automatically be run by test discovery. One final thing to bring up is there's something called test-driven design, which is simply a programming paradigm where you write your tests before you write the rest of your code. Now, that might seem a bit weird because you're like, how are you supposed to test your code if you don't know what your code's supposed to do? The reason this ends up being beneficial, at least from my view, is that it forces you to think about what you want your object to be able to do and how you plan on using it before you actually go and write the code for that object or for that class. Having been forced to think ahead about what your interface is supposed to look like and how it should behave is a really, really good thing because you now have an idea of how it should be used. You've thought about how your class should be laid out and what its purpose should be in terms of the whole before you've gone in and actually committed yourself and written all the code and potentially written it all the wrong way. You don't have to do test-driven design to get these benefits. It just requires that you think about what's supposed to happen and how you want to use your code before you use it. Especially if you follow the top-down design kind of programming pattern that we've been doing in class, you will get the same benefit as well. So that's a good thing to do and a good thing to practice. Now, I don't think I have anything else, but there might be one thing that's useful to point out is if you were doing test-driven design, you might not be ready for those tests to be run yet. So what you can do is you can mark your test with skip or skip ifs to say you don't want to run them and they won't be run, right? You can do skip, skip if, skip unless. So let's say we weren't ready to do this multiplying fraction and a bad thing. We could just put at unittest.skip, and now this function won't be run. So you can see that down here in test fraction, we're not doing that one, which is fine. There are also other things, again, if you look at the documentation, to check, to mark a test as you expect it not to be working. Like you know this code is broken and it's not functioning correctly, and you want to document that, but you just haven't gotten around to fixing it yet, you can mark it with another exception as well. Expected failure decorator, and it's gonna fail right here. And then this will make it be quiet until you finally get around to fixing it. So I plan on putting out a little short video about mocking probably later today. So take a look at that one when it comes out, but mocking is a lot more complicated than the basic testing, and you don't have to use it, but I kind of want you to have a basic idea of how it might be useful. I will see you guys all in class, and hope to see you there. Bye.